In this video, we will be working on Lesson 8.1, Chapter 1, Lesson 1. In this lesson, students will complete function tables and find function rules. Please get ready by opening your textbook to page 579 and get a pen or a pencil ready. Real world link on page 579. A ruby-throated hummingbird beats its wings about 52 beats per second. So this is a rate of 52 beats compared to 1 second. It says make a table showing how many times this bird beats its wing then in 2 seconds. Well, if I know in 1 second it beats its wings 52 times, what I'm doing is taking 52 times 1, so I'd get 52 beats. So if I am working with 2 seconds, I'm going to multiply 2 times 52, and I know 2 times 50 is 100, and 2 times 2 is 4, so it's 104 beats. So now it asks you to add to the table, how many times will it beat its wings then in 6 whole seconds? So if we have 6 seconds, we're going to take 6 times 52. So I'm going to do a little chicken scratch here. Times 6. 2 times 6 is 12, carry the 1. 5 times 6 is 30, plus 1 is 31. The hummingbird will beat its wings 312 times in 6 seconds. Now they want us to make a table for 20 seconds. So I'll put in my 20 seconds. I'm going to be doing 20 times 52. And to do that, I'm going to stack it up over here, 52, and I'm just going to multiply by 2 to start. 2 times 2 is 4. 5 times 2 is 10, excuse me. And then I'm going to multiply by 0. I get a 0 at the end, so it will be 1,040 times. In this next one, it says that a great hummingbird beats its wings 10 times per second. So make the table to show how many times the giant hummingbird beats its wings then in 3 seconds. So our rule has changed. Instead of multiplying by 52 as we did up here, this hummingbird is bigger and it beats its wings slower. It only beats its wings 10 times per second. So if the hummingbird beats its wings for 3 whole seconds, we're going to take 3 times 10, and we'll know that the bird has beat its wings about 30 times. What we were working on that last example is we are finding the output for function tables. Now function tables you have been using for a long time. There's this big fancy paragraph that outlines it, but I'm going to go back to everyday math. If you were in school in Rochester, you'll be familiar with everyday math. Remember the in and out chart? That if I put in 7, and the rule is add 9, if I put in 7, I'm going to get 16 out of the machine. If I put in the 37, I would add 9 to it, and out I would get would be 46. And if I put in 49, I'd add 9 to that, and I would get 58. Well, I could also reverse that. If I got out 18, now I would reverse the process. So I'd have to subtract 9. And so then I would say that I put in 9. Because if I put in 9 and add 9, I'd get the 18. So here for the 86, I'd subtract 9 to do the reverse to get from the output to the input. I'd subtract 9 and we'd actually get, let's stack it up, 86 minus 9 because I have to borrow. 9 from 16 is 7, and 7 is 7, so we put in 77. I bet this looks a little bit more familiar. Well, what we're doing here is, this is our rule, our function rule, and this over here is called the function table. So, a function is a relation, or like a relationship, that gives exactly one output value to one input value. So our function rule here in this example was adding 9. Whatever number I put in, the input, I'd add 9 to it, the function, and I would get one specific answer. 9 plus whatever that number gives me the output. So this is our function rule right here. And it describes the relationship between the in and the out. You can organize the input and outputs then and the function rule, the results, then in a function table, which I have here in this picture for us. When we're working with functions, this in is actually called the input. The out is our output as of today. We're going to get a little higher level with our vocabulary. Whatever we put in is called the independent value. This is our input. Whatever we put is independent because we can pick whatever number that we choose. Because we can just pick. The value then of the output depends on what gets put in. So the independent variable is the output, and it depends on what you put in and the function rule. So it's called the dependent variable. So let's give a couple of examples. If the output is 7 more than the input, so 7 more than is an addition sign, the input, and because I have that word than in there, I'm going to reverse this one. I'm going to say, and actually they use the variable x for the input. We rewrite it as x plus 7. We were working on this writing expressions in chapter 6. They want us to complete the function table for that relation, or for that, remember, that's a rule. Okay? So if our input is x, and we put in 10, I'm going to take 10 plus the 7. This is my thinking right here. This is my mental math. I know that my output will be 17. Just like they're showing us over here. I put in 10, so I do the math of 10 plus 7, and I get the output of 17. If I put in 12, I'm going to take 12 plus 7 and get the 19, just like they did over here. Same with for the 14. 14 plus 7 equals 21. So again, this is our input, or the independent variable. And the output, again, depends on what I put in, so it's the dependent variable. So here on example 2, they would like us to give it a try. They said that the output is, which means equals, 5 times the input, and they want us to use x for the input. So I can't use this multiplication sign. I'm going to put it like this. So it's like 5x. So there's our function rule. So we're going to take every input and multiply by 5. So if they give us 8, we're going to take it and make 5 times, let's back that up. If they give us 8, we're going to take that times 5 and get 40. If they give us the input of 10, we're going to take 10 times 5 and get 50. And if we put in 12, 12 times 5 is 60. So again, our input is x, and then we have our output, which is our dependent variable. So let's give a couple of these a try, and feel free to pause the recording and then turn it on to check your work with mine. So let's do this first one together. If our input is 4, and the rule is x take away 4, if I pretend that x is 4, I would subtract 4, and my output is 0. If I put in 7, I'm going to take 7 minus the 4, and I'll get 3. And if I put in 10, I'm going to take 10 minus 4, and I will get 6. Why don't you go ahead and try B, pause it, the recording, and check your answers and see if it matches mine. Do your answers match mine? Make sure you have your thinking here in the middle. 3 times 0 is, oop, I goofed. It is definitely not 3, it is 0. And 2 times 3 is 6, and 3 times 5 is 15. All right, so let's find the input for a function table then. Just like we did back on the front, where I worked backwards, we can do the same thing in a function table. Okay, so this is our x value, and now we're going to say that the output will be represented by the letter y. So here's my rule right here in the middle. What they'd like us to do is we need to go from 6, and we need to go across the chart backwards. What is 6? That's our final answer, and we had to figure out what number times 3 gave us that 6, because that will tell us what the input is. So we're going to use the work it backwards strategy to find the input. So we want to think of 3 times what equals 6. So it would be the same as reverse math, like what we've been doing here in Chapter 7. We're going to take 6 and actually do the opposite of multiplying. We're going to divide by the 3, and we get 2. So the input had to be 2. We can check our work here in the middle. 3 times 2, is that equal to 6? It sure is. Let's try the next one. If our output is 15, we need to figure out what number times 3 gives us 15. So we'll take 15 and actually do work backwards and do divide by 3, and we get 5. So the input had to be 5. So now I can check my work. Is 3 times 5 equal to 15? It sure is. Let's try the next one. If our answer is 21, I need to figure out 21 divided by 3, which gives me 7. And let's check our input. Is 3 times 7 21? It sure is. So when they give us the outputs over here, we actually have to work in reverse and work backwards. So let's try some of these. Now these are going to be trickier because we aren't just dealing with one type of operation. We have multiplication right here, and we have subtraction. So because we're going to end up doing our output and we're going to work backwards, we're actually going to have to do our PEMDAS backward. Subtraction, addition, division, multiplication, exponents, and parentheses. We're actually going to go in reverse order because we're working backwards. So when we look at this first one, if my output is 1, what is the opposite of subtracting 1? I'm going to have to add 1 to get 2. And now I want to know what number, we're going to take the 2, and instead of multiplying it by 2, we have to actually divide. So 2 divided by 2 equals 1. So let's check and see if our input is correct. If we take 2 times 1 and then subtract 1, do we get 1? Well, 2 times 1 is 2, and 2 subtract 1 is 1. So we are at the correct spot. Let's try another one. If our output is 3, I'm going to start by going backwards. I have to, instead of subtracting 1, I'm going to add 1. So 3 plus 1 is equal to 4. Now I need to figure out what number times a number gives me that 4. So we're going to work in reverse. 4 divided by 2 is equal to 2. So let's see if our work is right. Is 2 times 2 minus 1 3? It sure is, because 2 times 2 is 4. 4 take away 1 is 3. Alright, let's try 5. We're going to work in reverse. So instead of subtracting 1, we now add 1. So 5 plus 1 is equal to 6. And instead of multiplying by 2, we actually have to take the 6 and divide by 2. And we get 3. So is 2 times 3 minus 1 equal to 5? It is, because 2 times 3 is 6. 6 take away 1 is 5. So let's try another one over here on letter D. Again, we have two steps. We have multiplication and addition. So we're going to have to work backwards. So we'll be doing subtraction and then division. So we're starting with some bigger numbers here. We have 17. So if we have 17, working backwards, I'm going to have to, instead of adding 2, I will subtract 2. Sorry about that. And that will give me 15. And now I need to take 15, instead of multiplying by 3, I have to divide by 3. So 15 divided by 3 is equal to 5. So my input had to have been 5. So let's check. 3 times 5 plus 2 more. Well, 3 times 5 is 15, plus 2 more is 17, so I'm on the right track. Alright, let's try the next one. If our output is 20, working backwards, I'm going to start off by taking the 20. Instead of adding 2, I subtract 2, and I get 18. And then instead of multiplying by 3, I'm going to take 18 and divide by 3, and I get 6. So let's check and see if I'm on the right track. 3 times 6 plus 2 more. Well, 3 times 6 is 18, and if I add 2 more, I do get 20. Alright, let's try 29. The output is 29. I'm working backwards. I'm going to subtract 2 and get 27. And then instead of multiplying by 3, I'm going to take 27 and divide by 3 and get 9. So let's check it out. 3 times 9 plus 2 more. So 3 times 9 is 27. If I add 2, I do get 29. So putting it all together, now we're going to add it into a story problem. And we're going to actually be using the work backwards strategy that they're going to give us the outputs, and we're going to work back to the inputs with the rule here. But now we're going to add an extra step of adding this and graphing these points on a graph. So the Gomez family is traveling at a rate of 70 miles per hour. The function rule that represents this situation is 70 times x. So for every hour, x is going to be the number of hours. Make a table to show how many hours they will drive, how many hours it would take them to drive 140 miles, 280 miles, and 350 miles, and then graph the function. So they started by putting in the outputs, the 140, 280, and 350. Then they used the input, or the rule, to work back to the input. So they took 140 divided by 2, because we're working backwards. So we're going to use division. And they found it took 2 hours to drive 140 miles. The 280, they divided by 70, and they got 4 hours. And for the 350 miles, they divided by 70, and they got to the 5. So if you notice up here at the top, they've labeled this, that the inputs always represent the x variable, and output is y. And remember, on our graphs, the x's are down here on the horizontal, and going vertical is the y-axis. And when we make ordered pairs, we always write x, then followed by the y. So using our input table up here, we're going to pull out our input and the output to make an ordered pair. So the first ordered pair would be 2, then 140 for the y value. So down here you saw them go over to 2 on the x-axis and up to about 140. It's just a little shy of that line, and they put a dot, and that's your first point. For the 4 hours, the 4 represents the x, and the 280 will be your y value. So I'm going to go over to 4 on the x value, and then up to about 280 and place a dot there. And the last one, they said, was 5 hours at 350, and it took 350 miles. They could travel 350 miles in that 5 hours. So our next point then was to go over to 5 and up to 350. And then it's important, and they don't have it on here, but I prefer it that when my students get those 3 points, they draw a line connecting them. And you know you have a good answer if you can make a nice straight line like I did, connecting all 3 points. So let's give it a try. Brianna bikes 12 miles every hour. So the function rule that represents the situation is 12 times x. And x is representing the number of hours that we're biking. So x equals the hours. Make a table to find out how many hours she has biked in 12, 36, and 48 miles. So the miles is over here on the output, and the hours goes on the right because it's x, and we said that x was representing the hours. So this is our hours, and this is our rule here in the middle. So they're giving us all the outputs. They're telling us that she has gone 12, 36, and 48 miles. So to work backwards on this one, because it's multiplication, we're going to have to work backwards to our input. We're going to have to use division, the opposite. So if we start with the 12, 12 divided by 12 is equal to 1. So we traveled for 1 hour. So checking our work, is 12 times 1 equal to 12? Yes, it is. Let's try the next one, 36. Working backwards, instead of multiplying, I'm dividing. I'll take the 36, divide by 12, and I get 3. So my input is 3. Checking my work, 12 times 3 is 36, so I know I'm correct. On this last one, we have 48. So working backwards, instead of multiplying by 12, I divide by 12, and I get 4. So 12 times 4 indeed is 48. So now that they want us to graph this function, so we're going to have to make ordered pairs. So I don't have a lot of room over here, so I'm going to go down here at the bottom. Remember, here's our x and our y, and we always start with our ordered pairs x, y. So the first ordered pair would be 1, 12. The second one would be 3, 36. And the third one would be 4, 48. So I'm going to switch screens. We're going to actually plot these on a graph. So here's the chart all filled out for you. Right next to it, I hope you have written down those ordered pairs. Let's do it again if you haven't. 1, 12. So I'm going to go over to 1, and I'm going to go up to 12. And that's just a little bit past the 10. So I'm going to label it 1, 12 on my graph. My next one is, ordered pair is 3, 36. So I'm going to go over to 3 and up to 36, which is just a little bit past the 35 right there. And I'll label it as 336. And my next ordered pair is 4, 48. So I go over to the 4 and up to 48, which is just a little bit shy of that 50, and label it 4, 48. And like I had mentioned, I like to have a line connecting these all. And there we go. So now go ahead and go to your gold card and get the practice assignment. Good luck, and if you're having trouble, come see me.